In section 9.2 of your text, the concept of equivalence is brought up. Equivalence is a means of expressing the concentration of electrolytes in solution. Now, we've looked at electrolytes in class. You recall that electrolytes are substances that dissociate. That means they split apart in water to produce ions. These ions are able to move in solution, and the presence of these moving ions in solution enables the solution to conduct electricity. In other words, the solution is referred to as an electrolytic solution. An example of a very important electrolytic solution is blood. If you take a look at the major electrolytes present in blood plasma, you'll see that the major cations present are sodium, potassium, calcium, and magnesium. The major anions present in blood plasma are chloride, hydrogen carbonate or bicarbonate ions, and monohydrogen phosphate ions. So these would be the major electrolytes, cations, and anions present in the blood. Notice that equivalence is defined as that amount of ion which furnishes 1 mole of positive or 1 mole of negative electrical charge. So with that in mind, we can take a look at electrolytes that are present in the blood and write an equality, a relationship that exists between the mole amount of the ion and the equivalent of the ion. And it's directly related to the charge that is present on the ion. For example, 1 mole of sodium ion. How many equivalents are present? Well, sodium is a +1 cation. So 1 mole of sodium ion would furnish or produce 1 mole of positive electrical charge. So notice the equality. 1 mole of sodium ion is equivalent or equal to, I should say, 1 equivalent of sodium. And you can take that equality and write it as a conversion factor. 1 equivalent of sodium ion is present in 1 mole of sodium ion. It produces 1 mole of positive charge. So with that in mind, we just take a look at what the charge is on the ion, and that tells us how many equivalents are present. 1 mole of magnesium ion has a +2 charge. That is equal to 2 equivalents of positive charge, or 2 moles of positive charge. Therefore, 1 mole of magnesium ion contains 2 equivalents, or 2 moles of positive charge because of the +2 charge, and you can write that as a conversion factor. There are 2 equivalents of magnesium +2 ion present in 1 mole of magnesium +2. Let's take a look at the several major anions that are present in blood. Chloride is a major anion. Monohydrogen phosphate is a major anion. And again, looking at these charges, 1 mole of chloride ion produces 1 mole of negative charge, or 1 equivalent. So you can write that as a conversion factor. 1 equivalent of chloride is present for every 1 mole of chloride anion. The charge on monohydrogen phosphate is -2. That means that for every 1 mole of monohydrogen phosphate, you have a total of 2 moles of negative charge, or 2 equivalents. So 2 equivalents of monohydrogen phosphate for every 1 mole of monohydrogen phosphate ion. This is an important principle, and it is the reason why the concept of equivalence is used instead of just staying with the mole amount, which you are already familiar with. In any solution, the total charge of positive ions present has to equal the total charge of negative ions present. In other words, the solution has to be neutral. If that is the case, then that means that the total equivalence of cations present in the solution has to equal the total equivalence of anions present in solution, because an equivalent is 1 mole of positive charge or 1 mole of negative charge. So total equivalence of cations has to equal total equivalence of anions. Note this equality does not apply to moles, right? Mole amounts are not linked to charge. Equivalent amounts are. So if you take a look at table 9.6 on page 318, it gives you a breakdown of the concentration of equivalents that are present in blood plasma, also in very common physiological solutions used in healthcare, such as saline solution or Ringer's solution. Another very important and common electrolytic solution is Pedialyte, often given to people who are suffering dehydration, and it's important to maintain their electrolyte levels as well as to give them nutrients. So in Pedialyte, the major cations that are present are sodium and potassium, and the major anions present in Pedialyte, chloride ion and citrate ion. Notice this concentration expression, right? Because the amounts of electrolytes are much smaller than what we would see in typical mole amount or equivalent amount, concentrations of electrolytes in physiological solutions are expressed in milli-equivalents. So just bringing that dimensional analysis that we learned in Unit 1 to this expression, you know that the metric prefix lowercase m refers to a milli prefix unit. So this would read milliequivalents per liter of sodium ion, milliequivalents per liter of potassium ion. So looking at the concentration of sodium ion and potassium ion in Pedialyte solution, sodium ion concentration is 45 milliequivalents per liter of Pedialyte. Potassium ion concentration is 20 milliequivalents per liter of Pedialyte. And if you add those two values up, you get the total concentration of cations present in Pedialyte equal to 65 milliequivalents per liter. What we know is that must mean the total concentration of anions present in Pedialyte must also be equal to 65 milliequivalents per liter, because we have to have equal amount, equal concentration of cations and anions present in solution. And if you analyze Pedialyte, it contains a concentration of chloride ion equal to 35 milliequivalents per liter, and a concentration of citrate anion equal to 30 milliequivalents per liter. Adding those two numbers up, we get 65 milliequivalents per liter of anion, which is equal to the 65 milliequivalents per liter total of cation present in solution. So total milliequivalents of cations must equal total milliequivalents of anions in Pedialyte. Let's do an example problem to illustrate these concepts. What volume of blood plasma in milliliters would contain 0.00275 moles of magnesium ion present in it as dissolved electrolyte? And if you take a look at table 9.6 on page 318, they give you a range for the concentration of magnesium ion in plasma, and I'm choosing for this example problem to look at the high end of the range. So for illustration purposes, we'll state that the concentration of magnesium ion in blood plasma is 3 milliequivalents per liter. It can vary, and we're just choosing the high end of that range. Okay, let's look at this problem, right? We are told that this is the total mole amount of magnesium ion that we need to have present in the blood plasma. We are told that the concentration of magnesium ion in blood plasma, getting that from table 9.6, is 3 milliequivalents of magnesium present per liter of plasma. Here, we also looked at the relationship between equivalents and moles of magnesium coming directly from the charge on magnesium. There are 2 equivalents of magnesium present, magnesium ion present, per 1 mole of magnesium ion. So we'll need that relationship in this problem as well and write that as a conversion factor. So looking at our setup, starting out with a 0.00275 moles of magnesium ion that we need to have present total in the blood plasma. Well, our concentration unit is not in moles, it's in milliequivalents. So we are going to have to use the relationship between equivalents and moles in order to convert from moles of magnesium ion to equivalent. So looking at our dimensional analysis, our moles of magnesium ion cancel. We have 2 equivalents per mole of magnesium ion, and if we stop our problem right here, we know equivalents of magnesium ion that is needed. But we need to take that equivalent amount and convert it into milliequivalents in order to use our concentration properly. So the same dimensional analysis relationship that we learned in the beginning of the semester, prefix milli means 1,000. So there are 1,000 milliequivalents. Let's state that one more time. Prefix milli means thousandth. Let's state that properly. Prefix milli means 1,000th. Therefore, there are 1,000 milliequivalents of magnesium ion present in 1 equivalent of magnesium. So if we stop our problem right now, our equivalents of magnesium cancel, and we are left with milliequivalents of magnesium. We're now ready to bring in our concentration and use it as a conversion factor. Notice I need concentration of milliequivalents per liter to be used in its inverted form. I need to take this concentration and flip it so that milliequivalents of magnesium is in the denominator and liters of plasma is in the numerator. If I look at the dimensional analysis, the milliequivalents of magnesium cancel and I am left with volume of plasma in liters. But we need our answer to be in milliliters. So the last step of this problem, we've done this many times, is to convert from liters to milliliters. 1,000 milliliters is equal to 1 liter. Our liters cancel, and we have a unit of milliliters for our final unit, which is what we're asked to solve for. So taking our calculator and operating, just double checking that we've done this properly, and I get a value that I see needs to be expressed with 2 sig figs. So expressing this result with 2 sig figs, our concentration has only 2 sig figs to it. I'm writing 1.8 times 10 to the third milliliters of blood plasma would be needed to have 0.00275 moles of magnesium present dissolved in it.